Okay, now it's recording. Hi everyone, welcome to week 2 of probability for computer science. Okay, so last week we did probability, basics of probability, and this time's week 2 content. Okay, week 2 content mostly is to do with uh, conditional probability and independence. So last week everything was fine because most of the events that we were talking about were independent in nature. Okay, so independent nature events are often easier to work with because you can just multiply the probabilities. One does not affect the outcome of the other. So this time we'll be talking about conditional probability and independence. And another important part of that is Bayes theorem and law of total probability. Okay, these are this week's contents. So before I move to this week's contents, let's just revisit some of the interesting problems that we talked about. We left off last time, right? So here was the first problem. I'll just take a screenshot and paste it once again. Okay. So this was okay. I hope this is visible, right? So yeah. So here's the question. So the question says Ramu, the local drunkard, is standing one step away from the edge of a cliff. Suppose at any point of time, the probability of stepping away from the cliff is p, and towards the cliff is 1 minus p. Then what is the probability that he falls off the cliff when p is half? Okay, and so let me just draw that picture that we drew last time. Okay, here is Ramu. Okay, and Ramu is standing exactly one step away from the cliff. Okay, and so this is 1 2 3 4 5 6, and at any point of time he could move right, left, and so on. He could end up at this position some other time, right? At any point of time does not matter. The probability that he moves left is half is p 1 minus p, sorry, and the probability that he moves right is p. Okay, now question is, what is the probability that he falls off the cliff? That is, as soon as he reaches this point, distance equals 0. Okay, uh, he falls off. Okay, so in other words, the question is, he for example, in p is half. Okay, if he has half probability of moving right at any point, if he has half probability of moving left at any point, what is the probability that he reaches this point 0? So that is the question. Now I asked you guys for guesses, and uh, a reasonable guess would be something like 50 plus. A reasonable guess would be 50 plus something, 50 plus epsilon. Okay, where epsilon is not very large. Why percent? Okay, why? Because anyhow, Ramu at any point moving left, moving right is half probability. So if he moves with probability half to the left, then definitely he's going to fall off. Okay, so but there is still a small probability that he moves to the right. Okay, and then moves left and right, and then finally he lands up here, and then he takes a left and then falls off. But it somehow feels like the probability that happens is very low, right? It makes more sense that he always meanders around here, and since this part is infinite, okay, this part is infinite, he actually is stuck around here and he never falls. Okay, Kishore is also here. Hi Kishore, welcome back.
Hi, Bhavya.
Hi
Hello,
Kishore.
everyone.
Hi. And so yeah, for Kishore, I'll just repeat the question for your sake, because this question we stated in the previous session. Okay, The question is that a person, which we are calling Ramu, is standing 1 unit of distance away from a cliff. The probability that he moves left at any point of time is half. The probability that he moves right at any point of time is half. Question is, what is the probability that he falls off the cliff? That is, comes to distance 0 from the cliff. And there is infinite stretch of land to the right. Okay, so that is the question. So I told you, I spoiled the answer at the end by saying that, okay, the probability that he does is 100%. Okay, and today we'll prove it. Okay, today we'll prove it. So okay, let's see why that is the case. Now suppose, okay, x is the distance, okay, from the cliff. So that would mean that this is x is 0, this is x equals 1, this is x equals 2, and x equals 3, and so on. Right? So that is x. Now, what the question is really asking is, what is the probability, okay, that Ramu reaches x equals 0 when Ramu is at x equals 1. Right? This models the same thing. He is at x equals 1, he starts from here. What is the probability that he'll land here? This is the reformulation of the problem. Okay. Let me call this quantity x. Okay. Now let's see what that x is. Well, if Ramu starts from here, definitely with half probability he's moving left, half probability is moving right. So if with half probability he falls, so that is with half probability, that probability that Ramu moves left plus Ramu, okay, probability that Ramu moves right. Okay, not only does Ramu move right, and so what does he do on moving right? Well, he moved right, he reached here, right? And now with this new position, what is the probability that when he is right, he is at x equals 2, and then he falls? Okay, that's something like that, and then he falls. Okay, times probability that Ramu falls, given that Ramu is at x equals 2. I hope everything is clear. Okay, so is it like if he has x equals 0, he will 100% fall? That is the final answer. So finally, that is what we want to show. That is what we want to show. If he is at x equals 1, then he'll definitely fall. That is what we want to show. Okay, but for now we don't know how to get to that. We are slowly working towards the problem, but at least this much is sure, that at least half probability he'll definitely fall, because with half probability he's moving left and therefore falling. Right? So this is that half. Right? So probability that Ramu moves left at any point, we know that it is half, plus what is the probability that Ramu moves right? Half. Right? So this part is half. Now what is this? Now this is where the interesting thing happens. Okay, Ramu falls such that Ramu is at x equals 2. Ramu falls such that Ramu is at x equals 2. Okay, let's say Ramu is at x equals 2. First let me erase this guy. Okay, and let's say Ramu is at x equals 2 now. Okay, because with half probability he moved right. Of course, again he could go in arbitrary directions and so on. But what is the observation? Okay, let me again select this part. Okay, copy this and put it here. Right. Okay. Now, what is the main observation that we make here is that if Ramu is at x equals 2 and he were to fall somehow, he definitely needs to during some finite time he needs to reach x equals 1. right? So if Ramu is at x equals 2 and he's supposed to fall, he could be taking arbitrary paths, but definitely after some time he needs to reach x equals 1 and then reach x equals 0 and fall. Maybe he reached x equals 1 and then did all this business and then he fell also. That's okay, we'll handle that. But firstly, what we notice is that if he starts from x equals 2, he definitely, in order to fall, he definitely needs to reach x equals 1 first. Okay. Now is where the interesting thing happens. Okay. So this is nothing but half plus half times probability that, okay, Ramu reaches x equals 1. Okay. Given that Ramu is at x equals 2, right? That's what we said, right? He's at x equals 2. He definitely needs to reach here. And after reaching here, what happens? After reaching here, after reaching here, this probability, I mean, that he falls, is same as this probability that Ramu is at x equals 0. Okay, where x equals 1. Okay, Ramu is at x equals 1, and therefore Ramu reaches at x equals 0. Right? So that will be probability Ramu reaches x equals 1 times, right, when Ramu is at x equals 2, times probability that Ramu reaches x equals 0 when, okay, there's not enough room. Okay, x equals 0 whenever Ramu is at x equals 1. Okay, and what is this? This is x. Okay, this is x. Now what about this? What should this probability be? What is, okay, what should be the probability that when Ramu is at x equals 1, what is the probability that he'll reach Ramu, he'll reach x, sorry, Ramu is at x equals 2, what is the probability that he'll reach x equals 1?
Sir, the same as the falling probability, like half.
Exactly, exactly. Oh, wait. What did you say? The falling probability, which is?
No, sir. Like if he is x equals to 1, the probability of he will reach x equals to 0. Like the same probability will be
Ah,
here.
right. Which is x, right?
Yes, sir.
Yes. Now, what what Chauvin is saying is that if he is here, okay, uh, the probability that he'll reach x equals 1 is again x. Can you explain, Chauvin, the idea?
Yes, sir. Sir, the probability here we want to find that the Ramu is at x equals to 2, and what is the probability given that Ramu will reach x equals to 1.
Huh.
So he has to move one step left.
Yes.
And in the same way, if he have to fall, he have to move one step left from x equals to 1 to x equals to 0. So both probability are same, like we have to make one step left. So for that, there will be the probability equals to x.
Okay. I'll add some a little bit more to it, which is that if Ramu is at x equals 2, okay, so let me visualize it. Okay, duplicate and shift this here. Okay, so Ramu is currently at x equals 2. Now imagine that this is not what. Let's imagine that the cliff ended here. The cliff ended here. And we were saying what is the probability that when he starts at x equals 2, he'll reach x equals 1. No? But if the cliff ended here, then since this is infinitely stretching to the right, it is identical to the case that we started with, right? So it does not matter. It does not matter if it is identical to the cliff ending here. So it's in some sense it's equal to being at one distance from the cliff, except now the cliff is at x equals 1. Okay, so this is also x. Okay, it takes it takes time to convince yourself. So just let me know if that is clear or not. Okay. But what we obtain here is half plus half times x square, and you'll get x equals half plus half times x square. Okay. And then it's now just a matter of quadratic equation. Let's multiply both sides by 2. Now x square minus 2x plus 1 equals 0. Yeah, can you solve this equation and tell me what is x?
So it is the equation of x minus 1's whole square. So x equals to only 1 is the one and only solution.
Yes, yes, yes. So you can either use the formula, or you can notice that this is nothing but x equals 1 whole square. So which implies that x equals 1. So which is 100%. Okay. So we are using could you go the GP method? Okay, if we were to do the GP method, let's see. If we were to do the GP method, I would think that this would be equal to half plus half times, it's almost the same thing. So half times uh, here will be Ramu reaches x equals 1. So this will be half again plus one more. Sorry. So let me call this quantity t of reaching t of reaching 1 from 0 from 1 is half plus half times half plus half times uh, half plus t of, so moving, so he was at x equals 1, x equals 2, and either he moved left. Okay, so let's do one thing. T of 1, t of 0 comma 2. So Ramu started at 2 and then he fell, which is equal to half plus half times, just one more. Now we further expand this, right? So half times, either Ramu moves left from 2, which is half, and then you have t of 0 comma 1 plus he moves right, which is t of 3. He moves right with half probability, and then t of 0 comma 3, right? So, and this will infinitely happen, which is equal to half plus half times half of t of 0 comma 1. This part will repeat, the recurrence will repeat, plus now you will have an infinite sequence on this side, half times moving left. Okay, this will not be neat. T of 0 comma 2 plus half times moving right, t of 0 comma 4. You'll get something like this. I don't know whether there is a neater way to do this or not. Okay. So yeah, I don't know whether there's a neater way to do this or not. But the final sequence will be something like half plus half squared. Uh, there's this additional factor of t01 that will be causing an issue. Half. So Bayes theorem is used to solve the problem. I missed that part. Could you do the GP method? Bayes theorem also, you can use this. So what you need to do is, I think, yeah, rather than coming up with the GP, probably Bayes theorem would be more applicable. I mean, the GP will look something like, since you are assuming t01 here, so you will get something like 1 to the approximately. That's what I feel. This probably converges to 1 because this converges to like half, right? 1 by 2 square plus 1 by 2 square plus 1 by 2 power 4 and so on. This converges something to like half, and when you add these up, it should come to 1. Now, if you want to use Bayes theorem, let's see. So what do you get? You get this guy. Okay, let me copy this. Let's try Bayes theorem also. Okay. Copy. Okay. So this is what we have. So this we know, plus this we know, plus probability Ramu false such that Ramu is at x equals 2. So probability, according to Bayes theorem, probability that, one moment, probability that A happens such that B happens is something like probability of B happening given A happening times probability of A happening divided by probability of B happening. Right? Is this correct? Yes. Okay. Now this will be equal to probability that so Ramu false is A, so it will be Ramu is at x equals 2 such that Ramu false, and times, so this will be something, this will be was, see, and times probability of A, which is probability that Ramu false, and probability of B, which is probability that Ramu is at x equals 2. So probability that Ramu falls is like Ramu reaches x equals 0, and probability that Ramu is reaches x equals 2. But you will almost get the same thing. So now look at this. Relation. Okay. Probability that Ramu was at x equals 2 such that Ramu falls divided by probability that Ramu reaches x equals 2. So this probability will be nothing but probability that Ramu at x equals 2 and Ramu falls divided by, eventually falls divided by a times um, Ramu falls divided by Ramu reaches x equals 2. Okay. So we don't need to do this analysis. Yeah, so on.
Sir, you can do this right hand part in this way that like the ये part
Yeah, what?
numerator part,
Huh.
that probability of Ramu at x equals to 2 given Ramu false.
Yes, yes, yes. That's what.
You can you can write that in this way that probability of Ramu false given that probability of given that Ramu at x equals to 2 into probability of Ramu at x equals to 2 by probability of Ramu false. In that way, the whole part will become as equals to
It'll,
1.
it'll also, wait, whole part will be equal to 1.
So this right hand part multiplied with 1 by 2 will become 1 there. Then.
This part should not become 1. This part should be what we started with, no? Otherwise, we'll get two different answers. Because Ramu reaches x equals 0. This is this should be what we started with, no? I'm sorry, I did not get what you said. Sorry, so on.
Sir, I am saying the whole part. Sir,
Oh, you mean the whole part?
just write this one. Just write
Oh, okay,
the
okay.
probability of
I get it.
Ramu at x equals to 2 given Ramu equals to false into the base theorem formula, and the numerator and denominator will cut their self and it will get 1.
Okay. I think I get what you mean. So you mean so these two events need to be independent in order to do that. What you mean is probability that Ramu at x equals 2 times probability of Ramu x equals 0 or divided by x equals 0. This is what you mean, no? That is what you get here. And times
No,
probability that, yeah?
no, the
Go on.
new yes.
Right?
Yes. Just write the thing. Ramu reaches x equals to 0. Uh,
Right.
Sir, Ramu reaches x equals to 0 given Ramu at x equals to 2. So,
Given Ramu at x equals to 0.
sir,
Oh,
just
okay.
break this thing,
Yeah.
into the base theorem formula.
Yes. So this what you mean is this is Ramu x equals 2 times probability of, yeah, that's right. Ramu x equals 0 such that,
Given that, yes,
yes,
Ramu at x equals to 2.
Ramu x equals 2, right?
Hmm.
And you have this. Now additionally you have this multiplied by probability that, oh, okay, you don't need to do that. Now this,
No. I think this is not going anywhere.
let's see.
Sorry, sir.
No, it's okay. Let's just try. X equals 2. Okay, but there is circularity here.
Yes.
Yeah, we
Uh,
applied Gauss theorem and then we are sort of applying Gauss theorem once again.
we are getting the initial phase again. Probability of x equals to 0.
Yes.
X equals,
That's right.
yes. Sorry, sir.
No, it's okay. I think further than this, if we don't use the recurrence, there is no, because we are dealing with infinite probability, no. So this base theorem will keep on expanding. So I think what we can do is, I do not know a way of doing this without falling back to the first point that I was talking about. This. Okay. Oh wait, is there a, I think, latency? I changed my page. It's not reflecting on my screen. Is this, is anything I'm writing visible? Because on my end, okay, great. So this operation that I did, I think this is unavoidable even if we do use base theorem. That's what I think personally. Okay. So who asked the question? Um, Base theorem. Okay, Ankita. Yeah, right. So Ankita, I'll just leave it at this for now. Okay, because um, but I'll get back to you in the next class if Bayes theorem is applicable. Okay, Bayes theorem is applicable in some sense, but okay, but is this unavoidable? What we did here? Okay, and someone is raising hand. I think Harsh. Yeah, Harsh. Okay, Harsh says chat. Could you briefly explain the part where you showed that probability x equals 1 at x equals 2, such that x equals 2? I missed that part where you showed it was x. Okay, sure, no problem, Harsh. So I think up till here it's fine, right? Up till this point. Okay, okay. So if that is the case, then I'll say that okay. So the this is also fine. This is nothing but x. Great. What about this probability that Ramu reaches x equals 1 such that Ramu is at x equals 2? Okay. Probability that Ramu reaches x equals 1 such that Ramu is at x equals 2. So uh, Ramu is standing here at x equals 2, and there is x equals 1, and then there is a cliff. Then there are additional objects here. Now, we are saying what is the probability that Ramu reaches this point, given that at any point of time he can move left with probability half and right with probability half. So what we observe is, okay, Ramu is standing here at x equals 2, and what is the probability that he reaches x equals 1? Isn't this identical to the case when there is, I put an imaginary cliff out here in x equals 1 instead, and I say what is the probability that Ramu is at x equals 2 and falls off this imaginary cliff which is situated at x equals 1? Isn't the problem same? Because at any point he can move half, left with a probability half, right with probability half. At any point of and towards the right there is infinitely many steps, and towards the left, there is this imaginary cliff. So can't I say that the it is this restate the problem, saying that if he has at x equals 2, what is the probability that he falls off this imaginary cliff x at x equals 1? It is same as saying what is the probability that starting from x equals 2 he reaches x equals 1. Is that clear, Harsh? If Ramu starts at x equals 2, what is the probability that he reaches x equals 1? He could move in arbitrary ways, but what is the probability that he reaches x equals 1? But then I put this imaginary cliff, right. So it's the same thing because we are dealing with an infinite situation on the right. So I can equivalently say that it's as if I had a cliff here. It is as if even if I change this to x equals 1, x equals 0, which is nothing but the original problem, the count remains the same, the probability remains the same. And hence, this quantity is x. Right? Okay, great. Okay, great. So let's move on with the other questions. Okay. Oh, yeah. And please try now it's just calculate this for a general p. You will again get a quadratic equation and then plug in 2 by 3. You'll it's still surprising that even though the probability that moving away is 2 by 3, the probability still remains high. The probability of falling still remains. It need not stay 1, but it still remains high. Okay. So yeah, like I told you guys, this is called the one-dimensional drunkard's walk. So there is a two-dimensional version also. You can check it out, but the formulation is slightly more difficult. So that's why we are not doing it here. So instead of this one line, there is a lattice now. There is a grid, and the person can move, left, right, up, down. Okay, even diagonals you may allow with equal probability, and then the observation is that the probability is very high that you reach a particular node. Okay, you come back to where you started from, and this is used a lot in computer science. Okay, in randomized algorithms and in something called random walks on graphs. I think those who are from computer science background, they may have seen graphs, right? And if your graphs have a nice structure, you don't need to explore the graph too much to reach any particular node. With high probability you'll reach it. And it's used in for example, let's say you want to measure whether in Facebook, okay, whether this graph represents the graph of friendship, then is it possible to reach one friend from another in very few steps? Okay, something like that. Or Wikipedia pages, Google indexing and stuff like that. The indexing process, if it as long as Google randomly chooses pages, it can reach most of the pages in the internet with very high probability. Okay, so that is the kind of applications that this has. So this is a very nice observation. Okay, now let's yeah. So in case you are interested, then you can look into random walks. Okay, random walks and yes, stationary distributions. Okay, so um okay, this is, I wanted to like redo last time's questions, but it's okay. So yeah, so if someone had asked me, I don't know if it was Goyal or someone, to use Bayes theorem to do Monty Hall problem. So this is possible. Okay, so this is possible. I will not do it due to interest of time. I wanted to do it. It was Goyal, no? Yeah, okay. Goyal had asked. So
Yes, sir.
yes, good. So you can calculate the probability that the car behind door 1, given door 3 is opened, right? This is what we want to calculate. And then you can use the probability partition thing, and then finally you'll get 2/3. Okay, you can try this by yourself. Okay, so let's move on to this time's topics. Yeah, okay, good. So let's move to this time's topics, which is independence. Okay, it was done in week 2 lecture. Oh, was it? Okay, I think I didn't watch the final video of the lecture. Okay, yeah, thanks. So yeah, if you watch the lecture, which you should be doing, um, then yeah, you need not try this. Okay. So here is another good application. Okay, of pairwise independence. And by the way, what do you mean when event E1 and E2 are independent? What do you mean by this? Anyone?
Joint probability of E1 and E2 is equal to the product of the individual probabilities of E1 and E2.
That's right. That's right. And what is the uh, practical what to say understanding?
So I mean, one event is not leaving any impact over the other one. I
That's right.
mean,
That's right.
over the occurrence of the other one.
That's right. The occurrence of one does not affect the other. Good. Yes. So so that is probability of E1 intersection probability E2 equals probability of E1 times probability of E2. Okay. So when during high school when we learned probability, okay, probability E1 E2 are independent if that's what we said, but it's also an if and only if. Okay, so it means the other way around also. What that means is this is both necessary and sufficient. So if you want to check if they are independent, it is enough to check this particular fact. Okay, not just one way. Okay, so good. So where is independence used? Well, one important place where it is used is in in computer science in a concept called hashing. So hashing, okay, is to do with quick memory access. Okay, what does that mean? Well, let's say you have 10,000 items, okay, accessed several times, okay, which is accessed several times, and some items may be accessed more, some items may be accessed less. We are not interested in that case. We are assuming that the probability that you will access them is sort of equal, uniform distribution. Okay, and well, what can you do? Well, you can, and let's say you take the 10,000 slots. Okay, 1 2 3 4 and so on till 10,000, right? You can 10,000 slot, and you if one shows up, then you'll put it in the first slot, and if two shows up, you'll put it in the second slot, and so on. The issue with this is if there is a high lookup time. So if how do I know whether I mean, given a random access machine, I agree, okay, but if I'm not given random access, then I need to go through each of them, across each of them, and check. Now let's say I have random access, but usually random access is limited to smaller memory, right? The RAM is small, hard disk is large, right? So how do I settle in that? For example, in my RAM I have let's say 100 slots only, and the rest I need to do a linear search. Okay, so how do I take care of that? So in that case, I can use something called hashing. What does hashing do? Hashing puts these 100 slots, okay, has these 100 slots, and each of these 100 slots sort of represents a bucket of values. Okay, and so 10,000 divided by 100 is 100. So each bucket is of size 100. Okay, so let's say one um, uh, um, item comes, I'll put it in the first bucket. Then the second item comes, I'll put it in the second bucket. And the third item comes, I'll put it in the first bucket. And so on. Right? Now, the issue is I want to be fair to all the buckets. So to all the elements. I cannot unfairly put things in like most of the things in the last bucket. How do I make sure that I do this allocation carefully, okay, such that given a random entry, I'll put it in the correct bucket. So if two items fall into the same bucket, that is what is called a collision, and that is where I'll pay the price. Because as long as they fall in two different buckets, I'm fine. I so you get this concept of balancing out, right? I want them. I want these entries to be in as different buckets as possible. So that is where this concept of hashing comes in. Okay. So here is the question. Okay. Yeah, Tathagat. This is the question. Okay. So two distinct keys are hashed independently and uniformly at random into 100. Okay. So let C be the event that two keys collide that are hashed into the same bucket, and D be the event that at least one of the two keys is hashed into bucket 17. Compute PC and PD, compute PC equivalent D, and are event C and D independent. Okay. So let me just copy. Okay. So I have 100 buckets, 1, 2, 3, and so on. I have 100 buckets. Now keys are hashed independently and uniformly at random. Okay. And C is the event that two keys collide. So K1, K2, okay, hashed into buckets uniformly at random. Okay. And C is that the two keys K1, K2 collide. That is, they get the same bucket. And what is D? At least one key goes into 17. Okay. I want you to compute PC and PD. So can you tell me what PC is? What is the probability that K1, K2 collide?
So I think it should be 1 by 100 into 1 by 100.
Okay, so one says 1 by 100 into 1 by 100. So probability that the two keys collide is 1 by 100 into 1 by 100. Okay, others? Okay, Goel agrees. Okay, everyone is this the answer? Yeah, Harsh, Ankita, Kishore. Yeah. Okay. So okay, this is not correct. So one, can you detect why?
I mean, this would be same even if both do not collide. I mean, just drop any key out of the 100 buckets, the
Okay.
probability would be 1 by 100. So this is the joint probability of what? Joint probability of two keys are there in a 100 bucket, but
Hmm.
not the same. Sameness is missing here.
Same. Yeah. Well, I mean this is doing something a bit extra. Harsh is saying 100 divided by 100 C2. 100 divided by 100 C2. So you are choosing pairs. You're choosing pairs, and out of which 100 are good for you. That's what I think Harsh is saying.
So I think I got it. Can I share?
Yeah.
So the first will be going any bucket is 1 by 100. The second key is not going to that bucket other than any other bucket. So that should be 99 by 100.
No. They should call. Okay, not going. Yeah. Okay. Sure.
Not going. And substituting that from 1, like 1 minus that whole value.
Okay. The first step is still an issue. Is the what the first? Why should first be? Yeah. Well. Right. Should be 1 by 100 only. Because the only constraint is that the second key should follow the first key. No, second key should be mapped to wherever the first key was getting mapped to. K2 should be mapped to wherever K1 was getting mapped. K1 has no such restriction. So when you say the first 1 by 100, what is this probability for? Right.
Taking any bucket by key 1.
But it could go into any key. It has no restriction.
Yes.
So this is this probability should be something like 100 by 100. This you can justify saying that okay, it lands into some bucket.
Okay.
It lands into some bucket, and K2 definitely lands into that bucket out of 100 many where K1 had landed.
Yeah, 1 by 100 should be the PC.
Right? Ankita says 1 by 100 should be the probability of K1 goes to bucket 1 only. Yeah, right. Exactly. Okay. Yeah, Harsh, is this visible? Yeah. Okay. So Harsh, you said Harsh said 100 by 100 C2. This would be correct if he does not take 100 C2 and he takes 100 square instead. He takes 100 square instead. Okay, then you can do it. Okay, yeah. Harsh, your direction is also correct, but this 100 C2 should not be there. I think I get what you mean. It's like if I have like instead of 100, if I have 10 buckets. Okay, so let me take the sample space. Sample space is the first key gets mapped to first place, second key gets mapped to second place. First key maps to first place and second key gets mapped to second bucket. First key gets mapped to first bucket, second key gets mapped to third bucket, and so on until something like first key gets mapped to third bucket and second gets mapped to seventh bucket, and so on till 10, 10. So this is my omega sample space, right? So what is the size of omega? It is nothing but Cartesian product of 10 cross 10, right? So which is 10 square, and out of which I am only interested in 1, 1, like 2, 2, 3, 3, and so on, right? Yes, Harsh. So which is 100, which is 10 by 10 square, which is equivalently in here it will be 100 by 100 square, which is like again 1 by 100. Okay. So yeah, good. Okay. And yeah, Ankita was saying 1 by 100 should be probability that K1 goes to bucket 1 only. I fix the bucket, then yes, it is 1 by 100. Okay. So this is 1 by 100. Okay, good. Now compute P of D. Okay. Compute P of D. What is the probability? Okay, so what is D? D is the event that at least one of the two keys is hashed into bucket 17. Yeah.
Sir, we can break probability of D into 3 parts. Like both are going to bucket 17, or at least one of them are going to bucket 17.
Both of them are going into bucket 17, or at least one of the. Sure, but that is you can break it into even a simpler problem.
Okay.
Okay, so you said break it into um, both are going in the same bucket, or exactly one of them is going into the same bucket, right? Sorry, both are going to 17, or exactly one of them are going to 17. That's what you said, right? Meant by at least.
Yes, sir. Yes, sir.
So, yeah, can you actually, yes, 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 using complements, right? Yeah, good. Well, so what is the complement of event D? What does it? What is the complement of event D? What is the opposite of at least one of the two keys are hashed into bucket 17?
Like no keys in the bucket 17.
Yes, that is simpler, right?
Yes, sir.
Yeah, good. So D is at least one key goes to 17. D complement is none of K1 or K2 goes to bucket 17. So probability of D complement is equal to, so K1 does not go to 17, so there are 99 many options for it, times K2 also chooses one of the 99 other options. They could be same, not a problem, but definitely they should not go to bucket 17. This is D bar probability. What we need is probability of D. Probability of D goes 1 minus 99 times 99 by 100. So what is 99 times 99? Can anyone tell?
9801.
99 times 99 is 9801. Is it? 801. Yes, should be by 100. Right? So this should come to 199 by this, right? Okay, good. So this is the
Like,
probability. Yeah. So
sir, it's either way possible. Like I was saying the previous way. Like both are going to bucket 17. That
oh
will be
yeah,
1
yeah,
by 1 by 100
yeah, yeah.
plus at least one of them are going to 17, 1 by 100 into 99 by 100 into 2, because
Got
that
it.
will
Yeah,
be two
yeah, yeah,
tests.
yeah, 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 yeah. That'll also give you the same answer. Yeah, yeah,
Yes, sir.
yeah,
Give
yeah.
me
I was
some.
not saying it was wrong. Yeah, yeah. So yeah,
No
yeah,
problem, sir.
yeah, 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 yeah. Okay. So compute probability that C given D. C given D. Okay. So probability, conditional probability formula is probability that C intersection D divided by probability of D. Yes. Can you tell me? So here is the. Huh. So what is this equal to? So what does probability C intersection D represent?
Sir, the answer I am getting is 1 by 199. I don't know it's right or wrong. It should be right, but I am getting
By
this answer.
199. I think that's correct. Sure. You did it this way only.
Yeah, C intersection D is only way possible that both are getting to bucket 17.
Yes. 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 Yes.
That's the only case.
Right. Right. So C intersection D. Right. C is that both are going in the same bucket. That is both collide. And D is that at least one of them are going to bucket 17. So if both collide and at least one of them go to bucket 17, then it means that both are going to bucket 17. Right? I hope this is fine. So both are going to same bucket. one of the buckets is going to 17, then it means both of the buckets are going to 17. Okay, so this is probability that K1, K2 both go to 17 divided by probability of D, which is 199 by 10,000. 199 by 10,000. What is the probability that both go to 17? Now it is 1 by 100 by 1, right? And 199 by. Why is it 1 by 100 now? Because now we know which bucket to go. We are fixing the bucket where even K1 should go. Okay, and this is 1 by 100.
Yes, there we are having only one choice. The bucket
Yes.
17 is the obvious choice.
Yes, that's right. Right. So now the final part of the question is: are events C and D independent?
No, sir.
No. What about others?
So what's the probability of this C by D? The probability of C by D. What's the final value? The
C
probability
by
of
D.
C given.
Oh, D given
Probability
D.
of C
Oh,
given
C
D.
given D is 1 by 199.
And what's the probability of C? That value is 1 by 100. So that would mean that having the evidence C is making an impact.
Yes. Yes.
And so since this is making an impact, so both are not independent.
Both are not independent. That's right. That's right. And so yeah, Ankita is saying P of T is 1 by 100 square, right? No, Ankita. It's this. P of D is this. What is P of D? What is meant by D? D is at least one key goes to 17. No, at least. If it was both key go to 17, then it will be 1 by 100 times 1. The fact that both of them can go to 17 or any one of them can go to 17 makes the calculation not straightforward. I agree that it's 1 by 100 times 1 by 100 for probability that both of them go into 17, which we calculated here. Probability C intersection, which is probability C intersection. Is that clear, Ankita? Okay. Okay, got it. Right. So, yeah, what were you saying? Well, okay. Oh, yeah. So, yes. So there are two ways to do this. Either do probability C intersection D equals probability C times D or not, or like you said, you can check if probability if they are independent. If they are independent, then C intersection equals probability of D. Is not equal to probability. C intersection is not equal to probability C. Right? So that's what you meant, no? Go ahead.
Yes.
Yeah. So the fact that we are restricting it to both of them to go into bucket 17, okay, the fact that they'll collide is 1 by 199. Okay, so which is a good thing, which means they have a very low probability of actually colliding. And why does this happen? Because the hashing are independent and uniform. Everywhere, actually, implicitly, we are assuming that they are uniformly hashed. Okay, we are saying that probability of any key landing on any bucket is 1 by 100. So this is already assuming uniformity. Okay, but in practicality, to come up with purely random, purely workable hashing method is actually uh, important, data structure design question. Okay, and which we'll see now. Okay, pairwise independence. Yeah. So this is the question. I'll just take a screenshot and copy it. Okay, here's the question. Three fair coins are tossed independently. Okay. Now let A be the event that the first and second coins show the same outcome. B be the event that the second and third coins show the same outcome. And C be the event that first and third coins show the same outcome. Compute probability A, probability B, probability C. Okay. So before we do A, let's just what is the sample space?
Having 8 values.
Having
8 values, eight outcomes.
8 values, where what will be the contents?
So HHH and then
Yes.
HTH, that sort of thing.
HHH, HH,
T.
T, HTH, HTT, THH. Okay, let me write this below. THH, THT, TTH, TTT.
And
Okay.
now we can find which two, I mean, the A's, B's, and C's, these
Yes.
values easily. Yeah.
Yes, yes. So probability that A occurs is first and second coin show the same outcome. So
One by two.
yes, should be
4
one.
by 8. 4 by 8.
Yes, 4 by 8, right? So this one, this one, this one, this one, right? So it will be 4 by 8, which is 1 by 2. Okay, great. What about BC? Probability of
Also,
B and probability C. Yeah.
also 4 by 8. Also 4
Yes.
by 8.
Yes. So it's identical. It's symmetric argument. So it's identical up to rearrangements. No? Great. So we found PA, PAB, PB, PC. Now, what about this second question? Okay. Determine whether A and B are independent.
So let us come.
Yes, yes, they are independent.
Yes, they are independent. Okay. Why?
Sir, probability of A is half, probability of B is half,
Yes.
and A intersection B will be both first and second coin giving the same outcome, and second and third giving the same outcome. Like first, second, third, both all three given the same outcome.
Yes.
And that is only possible head or tail.
Yes.
Like it is 2 by 8, like 1 by 4. And if we multiply probability of A into probability of B, that will be also 1 by 4.
Good. So let's see if A and B are independent. Okay. Is this the case? That's what we want to check. Okay. And okay. Also, can anyone give an intuitive reason why A and B are independent?
So, in fact, all the three events are independent of one another.
Okay, but let's just talk about A and B for now. But why? Yeah, why?
Yes.
So it's already there in the question itself, right? They are tossed independently.
They're tossed independently, but the events are not whether one is head or other is tail. Not just that. It's whether A and B are no, A is the situation when first and second coins show the same heads, tails, whatever. Second and third is the event when they are tail. The independence is when um, the individual outcome, whether first is heads, does not the first toss is heads does not determine whether the second toss is.
Yeah, of course, I understand that. But
Yeah.
see, let us suppose A and B we take both the events.
Huh?
So before B event is performed, A isn't A event is already performed, and then we got the result.
Yes.
So, and when we perform the B event, right,
Huh?
we don't even care about the outcome of the
Okay.
A.
See, Kishore. A and
Yeah.
A event is not that the first coin is tossed. B is not the event that second coin is tossed. C is not that the third coin is tossed. These tosses have already happened. T1, T2, T3. A is the event that first and second coin are seen. B is the event that second and third coin are seen, and so on. So when you say when we do the B event, A is already done. That is not the case, because A and B are not the situation, the events of tossing coins 1 and 2. Do you get what I mean?
Okay.
You get what I mean, no, Kishore?
Yeah. Yeah.
So question is, why is A and B independent? No need to. We'll look at the mathematics, but what is the intuitive reason?
So it's a perfect example that non-mutual exclusive events, but also independent.
Yes, but give me an intuitive reason. Come up with a example, or come up with a counter example in this case. So okay, I'll just give you like a few more moments to try. A is the event. Okay, listen to this carefully. A is the event that the first and second coins show the same outcome. B is the event that the second and third coin show the same outcome.
So because first and the third, is independent.
Okay. Okay.
So since first and third is independent, so therefore the first value is not affecting the third value,
Right. Right.
and second value as such remains same.
Right.
So
Right.
these outcomes could have been different if the first outcome somehow is affecting the third outcome, and which
Yes.
is not the
Yes.
case here.
Yes. 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 So yes. So I'll again restate what Goel said. Okay. Event B does not depend on whether A shows right. Yeah, Ankita, yeah, said well. Exactly, exactly, exactly. Event when we say A and B are independent, we can think of the mathematics later. Okay, that A intersection B equals P of A times B of A. But understand the fundamental meaning of independence. One event does not affect the other. So when I say event A has happened, okay, so event A has happened. If they were dependent, then if A and B were dependent, then okay, A and B are dependent. Okay, then event A happens, then B is affected. Right, A happened, then B is affected. Either one of the things should happen. Either B does not need to, it definitely does not need to happen, or B definitely does not. But let's say event A has happened. So for example, what is A? First and second coin. No, first and second coin. First coin is heads. Second coin is heads. Okay. What is B? B is the event that second, third coin are same. This is not necessary. No, the third coin is an independent toss. So first coin is on heads, second coin is on heads, the third coin. This event, so first coin being heads and second coin being heads, which is event A. Okay, definitely has happened. Third coin can be anything. Third coin can be heads or tails. It's not affecting in any way. Right. The same thing if first coin was tails, second coin was tails. It's not that the third coin needs to be tails again. Third coin needs to be heads again. It's not necessary that event B happens. Right. Event B definitely happens. It's not necessary. Similarly, you the other way around also. Okay, since we are saying A and B are independent, and event B has happened. That is the third coin and the second coin are the same. Then A is affected. That is not the case. The first coin could have been anything. It's not necessary that the first, because the second and third coin are the same, it's not necessary that the first coin also needs to be the same as the second coin. Is that clear, everyone? Kishore, Goel? Yeah, Goel, yeah. Goel, sorry.
Yes.
Yeah, Goel understood, yeah. Shovan, Kishore?
I wanted to say, I mean to say same because
Huh.
once A is happened,
Huh.
so when B is going to happen, it doesn't check for what the result of A. It may be head or tail. That was I meant to say.
But Kishore, the issue that I had with the statement was that event A and B and C are not happening one after the other. But I think I think you meant the same thing, right? But
I mean, see, for just for the explanation, I have taken as A is happened and then B is going to happen next. But in the other way, also vice versa, also may happen.
Yeah, but you don't mean that they are happening one after the other, no?
Yeah, see, based on the outcome of A, B's outcome is not dependent on the outcome of A. That's what I mean.
Oh, okay. Yeah, sorry, then I misinterpreted that.
No problem. Yeah.
Okay. Right. So, so where were we? Yeah. Okay. So clearly that is the case. But let's do it mathematically now. So probability that A intersection B, what is this? That A has happened. Okay. Probability that first and second coin match and second and third coin match. But this is nothing but exactly the case when heads and tails, right? Out of 2 to the 3 many possibilities, matlab 8 possibilities. Right? So 2 by 8 is 1 by 4. Okay, good. Probability A times probability B is, what did we do? 4 by 8, 4 by 8. So 1 by 2, 1 by 2 times 1 by 2, which is equal to 1 by 4. So yes, they are independent. Okay, good. Now determine whether the events A, B, C are mutually independent. Okay. Yeah. So mutually independent means that if in this case there are
three of them.
Yeah, Kishore.
Probability of A, B, C intersections.
Probability of A, B, C. Yeah, right. Probability of A intersection B intersection C is equal to probability A times B times C. Okay. And
No, sir, they are not mutually independent.
okay. So what are the probabilities coming to?
The probability of A intersection B intersection C is 2 by 8 because head and tail are only the cases where all of them have the same intersection.
Right.
And probability of A, probability of B, and probability of C all have the same probability 1 by 2. Yes. So if we multiply 1 by 2 3 times, it is coming 1 by 8.
Yes, correct. Good. So one of them is 2 by 8, the other is 1 by 8. So good. Now again, I want to ask, like, is there an intuitive explanation for this. Like I said about the previous part, B. What is the intuitive explanation for this? Why are they mutually independent? Mutually dependent. They are not.
I think the same answer as we discussed on for the
Yeah,
A and
go
B
on.
independent.
Go on. What is the
See,
answer?
outcomes of A or either B or the C
Huh.
does not depend on the other two. See, let us suppose outcome of C, if we take, it doesn't depend upon the outcome of B or A.
Huh.
Similar way,
No,
B
but
and A as well.
this time we are saying dependent. They are dependent, no, because this time the probabilities are coming different.
Okay, so because few of them are like few of the in the sample space, in the few of them are like matching, right? So maybe that is the case where they are.
Huh.
Sorry, I
See,
think
yeah,
what we have to determine whether the events A, B, C are mutually independent.
mutually independent, and by calculation, we said that they are not mutually independent; they are mutually dependent.
Yeah, they are mutually dependent.
Yeah, by calculation, right? But now,
Right.
what
So
is
we
the intuitive explanation? Yeah, Goel says first is third has to be H, no other option. That's right. So in the previous case we said, okay, we have event A. If event A happens, then B definitely needs to happen. That is not true. B can happen or B cannot happen. Okay. And similarly, if B happens, then A has to happen. That is not true. A can happen or A cannot happen. That's fine. But now we have A, B, C. Now we are saying A is happening and B is happening. Is C going to happen? Or C complement going to happen? Okay, is C getting fixed? Right. So that's what Goel also means. That let's say A happens. That is
I
the
think
first and second coin. So show the same. And B definitely happens. That is the second and the third coin show the same. So if the first and second coin show the same face, second and third coin show the same face, then the first and third coin, which is event C, definitely needs to happen. You get it? So yeah, okay. So what is the intuitive explanation? Uh, A happens and B happens, suppose. So A happens is something like the first two coins, and first two coins had something, and B happens is um, tails. Wait, B happens is second and third coin, no, but the second is already fixed to heads. So the second and third coin is head. So C needs to happen. So you have head. And if it was A happens, tails something, and B also happens, but the second coin is already fixed to tails. So it needs to be, if B happens, which is second and third coin are same, it needs to be something tails. Okay, then C definitely needs to happen. The first and the third coin have the same outcome. Okay, is that clear?
Sir,
Yeah.
there is something which I had observed from this problem is that
Yeah.
ABC are non-mutually exclusive, number one. Secondly, ABC are independent from each other, like pairwise.
Yes.
Like A and B are independent, B and C are independent,
Exactly.
A and C are independent.
Exactly.
But A, B, C together are not independent, they are
Yes.
mutually dependent.
Yes.
And lastly, the A, B, C, these three event covers the whole sample space, like all the possible outcomes which we can get from the toss of three coins.
A B, yeah, that's right. So A B C um, um, partition. Do they partition? Wait. No, they don't partition, but it covers. Yeah, covers the sample space. That's right.
There is intersection point, but they cover the whole
Yes,
space,
yes.
whole sample
Yeah,
space.
yeah, yeah. They don't partition, but they cover. That's right. So that is the point that I was about to come to. Okay. One moment. I think my. Okay. So pairwise independence does not always imply mutual independence. Mutual independence is a more stricter, okay, more stricter constraint. It is pairwise does not mean it's mutual. If it is mutual, does it imply pairwise? Is the other way around true? Just one moment. Okay, I'll charge my laptop. Hello. 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 Okay. You guys can hear me, right?
Yes,
Yes.
audible.
Okay. Okay. Sorry. I lost connection in the way. Okay. Okay. Great. So yeah. Okay. Thanks. I need to reshare. I think. Need join here to share screen. Start. Okay. Okay. Yes. So yeah. So does pairwise independent imply mutual independence? Hmm? Any idea? Oh,
No,
sorry,
sir.
sorry.
Pairwise
This is not
independence
true. This is
not
not true.
always imply
Yeah.
mutual independence.
Yeah. Showan, what do you say?
Yes, sir. I am just saying the same thing. Pairwise independence does not always imply
Yeah.
the mutual independence.
Yeah. Sorry. Yeah. So does mutual independent imply pairwise independence?
That should be true.
This should be true.
If something is mutually independent, no. If something, I mean, things are mutually independent, will they be independent in pair too? Yes, common sense says yes, should be
Should be
independent.
right.
Yeah.
Yeah. That's right. because um, let's see, how do we? Yeah, so here's how you can think of this. Suppose we look at, let's say, the contrapositive, okay, which means it is enough to prove that if not pairwise independent, then it is not mutually independent. And this is true because if you have A and B and they are not pairwise independent, means that A depends on B or B depends on A, then it also implies it is not mutually independent, because any, let's say you take something like A, C, D events happen, then since A is there in the set of events happening, it will affect B also. So since there is B depends on the set happening, it means that it is not mutually independent, right? Is that clear? Cool. Yeah.
Yes, yes, right.
Yeah. Okay. Shovan, this is fine, no?
Yes, sir.
Yeah. What did you say?
So the connection was just lost. Can you please repeat the question,
Yeah.
please?
I mean that it is true that mutually independent means not means pairwise independence, because just look at the contrapositive. It's enough to prove that if something is not pairwise independent, then if if the events are not pairwise independent, then the events are not mutually independent, right? This is enough, sufficient. So, for example, let's take a case when it's not pairwise independence. So there are two events such that like A causes B. Okay, so B is dependent on A, so they are not pairwise independent. Or it could happen that B causes A, it's equivalent. Okay, so let's take A causes B. Then if you take a set A, C, D happening, then since A happens, B should happen. But if this is the case, then it means that these events are not mutually independent, right? If you take omega equals ABCD. Or rather 2 to the omega, probably. Oh no, this is correct. This is correct. Yeah. Right? So what? So
Yes, sir.
yeah. So this is not mutual. So yeah, but pairwise independence. So explain the difference. Okay, this is mutual with an example. Okay, in this example, sure. But the main crux is mutual independence is even a stronger thing to achieve for. So and again in hash families, so there is something called k-wise independence. Probably we'll look at this in the later part of the course. How do we pairwise independence? Maybe we can expect to do easily. K-wise independence. How do you come up with k-wise independence? It's a stronger restriction. You come up with better hashing protocols using k-wise independence. But how do you come up with this? Maybe we'll see it at the later part of the course. Great. Okay. Now it's 7:40. So let's move on to base theorem. Okay. What are the questions? No? Oh, there are only 6 questions. I feel like there was one more, but okay. So here's another question. Okay. Which we can solve using Bayes theorem. So a spam detection system works as follows. Okay. 20% of all incoming emails are spam. Detector correctly flags a spam email with probability 0.9. The detector incorrectly flags a legitimate email as spam with probability 0.1. Let S denote the event that an email is spam. F denote the event that email is flagged by the detector. Okay, S is the event that the email is spam. F is the event that the email is flagged by the detector as spam. Okay, what is the probability that a randomly chosen email is flagged? So first tell me, before even we begin, what is the sample space here?
What is the spam email?
No, what is the sample space? What is the sample space?
I think sample space can be taken as 100%, which is in figure, if you say 100 emails, out of that 20 emails are spam.
Okay, yeah. So the sample space omega is a set of all
Yeah.
emails.
Right.
The sample space should be all incoming emails.
Yes, all incoming emails. Right. Or let's email. Okay, and yeah, it could be we can fix something like 100 or something. Right, that's right. Okay. Okay, good. So the sample spaces. Now it's about whether E is in spam or E is not a spam. Right. S is the event that email E is a spam. F is the event that it is flagged by the detector. Okay, as spam. Question is, what is the probability that a randomly chosen email is flagged? So since F is the event that an email is flagged by the detector, and a probability that a randomly chosen email, where is it chosen from? This sample space, right? Sample space of all event, all emails. So what is the probability of choosing an email and getting flagged? Probability of F. That is what they are asking, right? Right. Yeah. So can you tell me what is probability of F? How can we do this? Yeah. So let's just write some.
So what's yeah.
Yeah, go ahead.
So we can use base kind of the thing
Yes.
here,
Yes.
and then we can write that the probability of F is equal to the probability of spam multiplied by the probability of say the flagged F given the evidence of S. Probability of flagging it, and wherein it is known that this is spam. That sort of
Okay.
thing.
And
You
divided by
can divide it by the probability of what is left.
F. Good.
Not F. This formula is not correct base.
Oh wait, not F.
Yeah. In fact, so no denominator is required. Only numerator is sufficient, I guess. This is not the base, the direct applicability of. I mean, I'm not computing the probability of F given some evidence. No. The probability that an email is spam multiplied by that when I detect this a spam, if it is known that this is a spam, then what is the probability of flagging it? So no denominator is required. Yeah.
Well, I wouldn't say that. No denominator is required. What does base theorem say? Okay, wait
This
a minute. Let me clarify this. Ankita Giroti says if F contains email that is spam or not spam, but detect as spam. Uh, Yes, yes, Ankita. So F is F represents the set of emails that are flagged as spam, but they may be spam or not spam. That's right. That's right. Yeah.
So the first question we break it into two parts, like probability of randomly chosen email is flagged. The probability of flagged is uh, actually the email is spam and it's flagged, or it can be actually it is not spam but it's flagged.
It is spam but flagged.
Or it's not spam but flagged. Because it's flagging only the
Probability that
spam
it
emails,
is
no?
not spam
But flagged.
but flagged. But probability that it is flagged given it's not spam. Yeah. Okay.
Yes.
This
And
was
it's equals to probability of spam is 0.2 and probability of flag given spam is 0.9 as per given in the question.
yeah.
Plus probability of not spam is 0.8 into probability of not spam but flagged is 0.1. So the answer I am getting is 0.26.
Yes. Good. 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 That should be correct. So
So
let's yeah. Sorry, go ahead.
no, if this I just said that if this calculation is correct, 0.26, then this answers the second question as well, wherein I'll just pick the first part of the term in the right hand side and divide it by the P of F.
What given an email is flagged, what is the probability that it is actually spam? Yeah, so there we'll use base again, right? But yeah, let's just for a moment before we get into that, okay, let's just finish this part. So the probability that it is spam is 20%, right, according to the question. So which implies that probability that a randomly chosen message is not spam is 0.8. Now, probability that detector flags a spam with a spam email. Flags a spam email. So probability that you flag given a spam email is 0.9, and probability that incorrectly flags a legitimate email as spam. So if it is legitimate, which is not spam, but it is flagged
Not
as spam,
spam but flagged.
yes,
Yes, it should be 0.1.
0.1. Good.
Yes.
So this is what we have, and yeah, like Shovan said, probability that it is spam. So this is 2 times probability
Mm.
flag, but spam, given spam 0.9
0.9, yes.
plus 0.8 times probability that it is not spam but flagged
0.1.
which will come to something like 0.26.
0.26.
Yeah, good, correct. Yeah.
And after getting that, the second question is become very easy.
Yes. So now the second part is probability that an email is flagged. Okay. And what is the probability that it is spam?
Hmm.
Now at this point we can use base theorem, right?
Yes, sir.
So the probability, which is probability that flag and spam
Given spam into probability of spam,
divided by probability of flag.
probability of flag.
Yeah, I think this is what you meant, no, Goel?
Yes.
Okay. So which is probability flag given spam? What did we have? 0.9.
18 by 26, sir. I'm getting.
Okay. So and probability that it is spam is 0.2. And this is 0.26. Yeah, 18 by 26. Can you tell me in terms of percentage?
Yes, 0.692.
Yeah, okay, 0.692. So something like 70%. Okay. Now, so yeah. This is a simple example of base rate fallacy that you may I've seen the lectures, right? So you know that it is as if uh, the spam detector is very good, very efficient, right? Because correct flagging is zero point 0.9, right? If it is a spam, and it makes very little error if it is not a spam. So it looks like it is very, very good. But since this base rate, the set of all incoming emails are very small, I want a much better detector. Otherwise, it's working like uh, with a 70% efficiency, as you can see, right? Given that an email is flagged, the probability that it's actually a spam is actually, you know, lower than 90%. We'll see an even more extreme example next. Okay, but this is clear, right? Okay, good. Uh, okay, Ankita, good. Okay, Kishore, Harsh. Okay, others also it's clear, right? Dhanalakshmi.
So
Yeah.
since the denominator is something and which can play the role of a constant kind of a thing, so therefore this value can you scroll it down
Yes,
slightly
yes.
bit, yeah. So this value say probability of S given the evidence F is in fact proportional to
Hmm.
the probability of F given S multiplied by the probability of S.
Hmm.
Consider the case, say, had this been a situation like the probability of some other possibility and giving the same evidence. So this F is something which is constant kind of the thing. Uh, like say, so the probability of S given F, probability of S given F,
Ah,
probability of S given F is like uh, so like the classification problem. So in the classification problem, the probability of S and given F. Say I have marked something as I classified something as faulty,
ah,
and now this indeed is faulty.
ah.
So that is the probability of S given the F, and
Yes, yes.
so that will not. So since the denominator here is because like say a closely related concept is of naive base,
Okay,
which these ML people use.
okay.
So there they do not consider the denominator because they said that okay, this value is 26. This is going to remain the same in that sense.
Probability. Okay. So what you are saying is probability of F is constant. It's not going to change.
Yes, this is yeah in that sense, yeah.
Okay. Uh,
Because if you can understand this base the theorem through the Venn diagram,
uh, uh,
then if you can draw say two events A and B, say S and F, and if you can understand say like say there are two events say A and B, and then then what this probability of A given B is indicating, and then if you can write the formula. So initially the probability of A given B is the joint probability of A and B and divided by the probability of B. Joint probability of A and B and divided by the probability of B.
hmm,
So that would mean what? The intersection area and divided by the probability of V.
right.
So what is so that makes sense also. But then we write this probability of A intersection V in a slightly different form. Like say we used to write it as posterior kind of thing. That is probability of given A and then multiplied by
Yes, yes, yeah,
the probability of multiplied by probability of A and divided by the probability of B, sort
yeah.
of thing. So my point here is that A is my prediction and B is my data. Say
A is your prediction and B is your data. Okay,
yes.
so No, I think rather
B,
it's
B,
the
B
other
is
way
my
around.
B is my data point. Yeah, incorrect or in reverse?
Wait, here, see, you are saying flag, given flag, it is spam. It is actually spam. So B should be your prediction and A should be your data, right? That would be equivalent. Like
B
saying,
should be.
oh, this is like the algorithm says this is a spam is equivalent to saying this is my prediction, and actually being spam is like the actual data. Is it not?
Yes.
Yeah.
And that equals to that how many times when I make the prediction A, that corresponds to the data point B,
Yeah.
and multiplied by that how many times I am predicting A.
Mm-hmm.
That makes sense.
Right.
So it will not have any impact over the probability of this B, I mean to say. And what this B here is that I am observing this class, right? So in a data set, say if data set has been given having the multiple number of the data points and having say three classes C1, C2, and C3. So the probability of observing a class anyways is going to remain the same. Now the thing is that if I pick a data point, so what's the meaning of probability of A given B here? That I observe the class as C1. What is the data point and what is the classification here in case of A by B?
So what we said was this is the prediction.
Yeah, this is the
This is the
prediction
data.
and this is the data, right? So in the right hand side, it would mean that how many times, if the data is given to me, then how many times I make this prediction, and how many times do I see such a data, and how many times I'm going to make this prediction. This is something which is constant, anyways. This corresponds to the entire data set. That kind of.
See, that's what I'm not sure. It's not how many times. It's rather it's like what fraction of data, what fraction of items do I perform this particular prediction for? Okay, so for yeah, right. So what fraction gets predicted as X, B, whatever. But it's okay. Okay. I'll think about this. Okay. So what you basically mean is that this remains constant, right?
Yes,
Okay.
yes.
Okay. Okay. I'll look into this. Maybe we'll talk about it in the next
Yeah,
session.
sure,
Okay.
sure. Yeah.
Okay. Great. Thanks. So but okay. So it's almost 8. So I'll just quickly look at final question. Yeah. Okay. Sure.
Just can you go back to the same slide which
Okay.
you were discussing? Go ahead and
Okay. Yeah. Just one moment. I'll just copy this. Yeah. This one.
just a quick clarification. Yeah, of course. See, when we say probability of A given B, A would be the data point, and then B is the prediction, right?
Yeah. This is what I was doing according to Goyal's this thing. But yeah.
No,
Go on, Kishore.
yeah, that's true. But I just wanted to clarify myself here.
Yeah.
It's not anything. It's not a query.
Yeah.
Given the problem, what we have the problem. So A is the data, and then B is the prediction. So when we say when probability of A given B, but when we say probability of B given A, what B becomes and then A becomes that time.
Oh yeah. So yeah. This I was not very particular about. B is something like prediction is say it will rain.
No,
And
that I
data
understand. No.
data is
Bhavya, 1 second.
it
So
actually
this part I have understood.
rains.
So what the clarification I need is for probability of B by A.
Yes, exactly. So yeah, that's why I wrote this.
Oh, is
So
it okay?
A will be given that it actually rains, what is the probability that prediction said rain?
So actually, this probability of B by A is a training. Is the
Yeah.
training of the model.
Okay.
Yeah, probability of B by A is the training of the model, and probability of A by B, I'm making a prediction. And then this B actually doesn't matter here. I mean to say.
So B, yeah.
Is
So
that is the terms change when we say probability of A by B, or and when we say probability of B by A?
yes,
Is the
yes,
term
definitely.
changes, or is it, they remain same?
No. That the B by A and A by B are definitely different quantities, very different quantities.
Okay.
Okay,
Okay.
but what Goel is saying that this is not changing. I mean, I'm not totally sure. Also, like this, ML is not my area of expertise, but probability of B is like out of the data, what fraction of data is classified as rain. Okay, so you have several parameters: precipitation, humidity, things like that, wind speed, and so on. What fraction of that is classified as rain? Okay, is PB, right? Because B is the prediction that it will be, and P of A is so that is the prediction. Okay, what is classified as in predict, and P of A is what fraction of the data is actually rain. Okay, so what Goel is saying is that this is not going to change. So this is not
Yeah, yeah,
relevant.
yeah. Of course, Goyal's point I have understood, but
Yeah, but yes,
it's my point. I was just confusing. See, how to interpret. See, when we say with this
Mhm.
problem, respect to this problem, what we are discussing, how to interpret probability of A by B and probability of B by A.
Yes, they yeah.
That's where I'm getting confusion.
Yeah. They are different, very different. So um,
So if they are different, how to I mean to say interpret or determine them when
yes,
we wanted
yes,
to put in a sentence, right? Probability of A by B put into a sentence, and probability of B by A put into a sentence.
yes. So I mean, see, if I use the same example, like you want a different example.
Same example also okay, not a
Oh,
problem.
okay. So the see probability A by B is given that the prediction is rain. Is it, what is the chance that it is actually raining? Okay.
Okay.
So given that prediction is rain, what is the chance that it is actually raining? Okay. And this is given that it actually rains, what is the probability that prediction is saying rain? Okay. I think this is okay. This even this is not a good example. Let me come up with a better example. Okay. Let's look at the spam, not spam thing. Okay. Probability. Okay, it's already 8 o'clock. So please, if you are free to leave. Okay. If anyone wants to leave, then please you are free to leave. Okay. Let's look at the spam thing. Okay. So spam given flagged versus probability that flag given spam. Okay. So here, what is it saying? Probability that email is spam is spam when filter says spam. Filter says spam. What is the probability that it is actually spam? Versus probability that um, filter says spam when email is actually spam. these are two different quantities, because let's say filter set spam. Okay, let's say filter set spam. Okay, and what is the probability that email is spam? Okay, let's do the first one first. Okay. Here is a filter. Okay, here is a filter. Filter says, given any email, okay, mark as spam. Given any email, mark as spam. So it's it's a very bad filter. It's going to mark every filter as spam. Okay, it's going to mark every filter as a spam. Sorry, every email as a spam. That's clear. Every email is marked by a spam. It's a very bad filter. Okay. Now let's see this probability. What is the probability that, okay, given this filter, when email is actually a spam, what is the probability that it says spam? Kishore? When the email is actually spam, what is the probability that it will say spam for this filter?
0.9 times.
Not even 0.8. It's higher. It's 100%. Because
No,
for every
given
email it's saying spam. Huh?
no, but the it will flag only 0.9 mails, right?
No. Forget about that one, that example,
Okay.
that question.
Okay.
I'm saying this is a new filter, okay, brand new filter, which is hopeless kind of filter, which says any email it will mark as spam.
Okay, then 100%.
Then 100%. This probability, when it is actually spam, also it says 100%. Okay. Now let's look at this probability. Let's look at the other probability. When filter says spam, what is the probability that email is spam? Is this also 100%?
Can you repeat that?
If
Please?
for the same filter, when filter says spam, okay. Whenever, let's say, an email filter says spam, what is the probability that email is a spam? Is this also 100%? Filter says spam. Can I now confirm that the email sent was a spam because the filter said spam?
It cannot be.
It cannot be, because this filter is going to mark every email as spam, and it may so happen that it said spam to a filter, to an email which is not a spam because of the way it's designed. So
Yeah,
this is
got it.
definitely less than 100%. In fact,
Just-
it's
just-
equal to the number of non-spams. Yeah.
I got that. I
You
just
got
wanted to correlate with this concept, with the ML concept. I just wanted to clarification from Goel. Goel, is this related to confusion matrix?
No, not to the confusion matrix as such, but then there is one classification technique, and that is called the naive Bayes.
Navy
And-
Bayes. Okay.
Yeah, naive Bayes.
Yeah. No,
And
that
so,
is
yeah,
fine.
so
But this one, the point which I was asking, right? So if it is true and then a false, and then just like confusion matrix, is that the same?
yes, more or
Where I
less.
can relate that?
Yeah, more or less same. And since we use the confusion matrix as a measure to represent the accuracy of the model.
Okay, got it. I just for my better understanding, that's it.
Yeah. Similar to that. Even though it is already, I mean, we are already late by 10 minutes, but then P of A by B, my intuition is that A is the prediction and B is the data point, contrary to what we wrote earlier. So in the P A by B is that the probability of observing the class given the data point is equal to the probability of the data points given the class multiplied by the probability of observing the class and divided by the probability of observing the data point. Yeah. So, I mean, earlier in the slide when we wrote, so P of A by B, so I mean, that is my intuition. I did not refer to the precise this naive Bayes, but still, yeah.
Yeah.
भाव्य सर भी लाइक मैं तो प्रोबेबिलिटी पढ़ाने आया था, यहाँ पे मशीन लर्निंग कहाँ से आ गया?
Yeah, so
It's just for better understanding ourselves, because probably I think you are purely a mathematics background, but we ourselves we left mathematics a long back. So just to better understand ourselves, we are just trying to correlate with some of the known concepts. That's it.
yeah, no, that's right, that's right. Yeah.
No problem. I am also preparing for DA paper, so
Okay,
your
okay.
I just go through conversation of your and Goel and Bhavya sir, and I think it is very helpful for me also to
Yeah,
get the intuition about the classification regression problems.
yeah.
Thank you to you, to three of you both.
It's okay. You're welcome always. Even we learn a lot of things based on your discussions and then doubts. It's mutually.
Yeah.
Yeah, it's pleasure.
Right.
Sir, it's my first class. Can you introduce yourself like a way that I don't know you? I just seeing you for the first time. Uh, if you have no problem, please, sir.
No, you're asking me? Oh, okay. You were not there in the last class. Oh, okay.
No, sir. Due to technical issue, I was
Oh,
absent
okay,
in the
okay,
last
okay.
class.
Yeah. Okay. What shall I? Okay. I am a PhD scholar at IIT Madras. Okay. So, and I work in theoretical computer science. So more specifically, I work in something called complexity theory. Okay, and complexity theory deals with. Uh, I think Goel was there during when I taught complexity or not. I'm not sure. Were you?
Yes,
You
yes,
were there, no?
yes, yes. I
Okay,
was
okay.
there.
Yeah.
Both me and Kishore both were there.
Oh, okay. Yeah. Okay. So
So,
both of
so,
them.
so yeah. So we both were there when you taught complexity theory and the selected topics and algorithms.
Yes. Selected topics and algorithms also. Yeah,
Yes.
right. So my area generally lies around algorithms and complexity theory in more general. So complexity theory is it's a study of how to classify things into easy or hard. Okay, computational problems, whether they are easy or hard, and you may have heard about things like NP completeness, NP hardness, and stuff like that, right?
Yes, sir. NP hard problem.
Yes. So that exactly falls around my area. And more specifically, I work in something called space complexity. So where we study the complexity of problems with regards to space taken instead of time. And I also do algorithms. Okay, so I do some query algorithms and stuff like that. I like working with these kind of algorithms, and but mostly I do complexity. But I like anything that is to do with theoretical computer science usually. So that's what I do.
Sir,
So
as I know, there are some computational problems which we know that they can be solved in the constant time or the constant theory time, but their exact solutions are not exist now. So, are you trying to go in that field that trying to solve that problems in the constant time, and also the space should be limited, like optimized space, like in that way?
yeah, so see, it's like the following. Complexity theory is somewhat the opposite of algorithms. Okay, so algorithm says, okay, here's what we can do. Here's what we can do best. Okay, so okay, the previous bound was something like uh, cubic n to the 3. I reduce it to n square, or previously only exponential time algorithm was known. Now I've reduced it to polynomial time, something like that. Okay, complexity theory is the opposite. It's a pessimistic variant. What I mean by that is a complexity theorist will show that um, this problem, you no matter what happens, you cannot do better. No matter what happens, you cannot do better. Okay, and no matter you cannot come up with an algorithm. So these are called lower bounds in complexity theory. So this is the way. So it's like two ways to attack the problem: either show that you can do better or show that you cannot do better. There was this there was this researcher, this complexity theorist who actually came to visit in IITM, and he said that there are two ways to prove that you are smart. Okay, and what are the two ways? Well, the first way is that you take a hard problem and show the world that you can solve that problem. And what is the other way to prove that you are smart? It's to say that if I cannot solve the problem, then no one else can. Okay, so uh, that is the philosophy of algorithms versus complexity theory. Algorithm shows that okay, this is we can do better and better, and here's what you can do. But finally, if you encounter a problem where you cannot come up with better algorithms, then you say that okay, fine, here is a proof that shows that you can't come up with an algorithm which does better. And it's lower bounds are incredibly difficult. I think a good example is something to do with comparison sort algorithms. Okay, for example, bubble sort, selection sort, merge sort, where you compare element by element. If you cannot, or rather, I'll say any algorithm takes at least n log n time. No matter how good of an algorithmist you are, it is not possible to come up with an algorithm, that a comparison sort algorithm, that does better than n log n time. So there's an information theoretic proof for this. So this is somewhat what a complexity theory result looks like. You get it?
Okay, sir.
Yeah. But the line is not very clear. It's there is merger between algorithms and complexity every time. But yeah, there are some very interesting things that are there in complexity. There is an NPTEL course also. I think Goel is crediting it this time. Also, I think Neha is taking the solving sessions for that, right, Goel?
Yes. This time I am taking sessions of TOC as well, theory of computation.
Oh, TOC. Yes, sorry, not complexity. Yes, this time is taking TOC. But yeah, complexity. I think you took last sem or something like that. Maybe, I don't know. Oh no. Regardless, there are some very interesting things in complexity. You can check that out sometime.
But just one clarification. Probably you may say it in yes or no.
Yeah.
See, when we say this algorithm, right? You say the shortcut. I mean, like we cannot reduce furthermore like lesser time
Yeah.
than n log n, right?
Yes.
So is it something specific to one environment? See, let us suppose now we are getting into the environment of or the era of this one, right? What do you say? The computational part. What do you say? I just it went out of my index. Quantum computing.
Quantum, yeah.
So is this remains same? The time remains same for even the quantum environment?
Yes. Even in quantum environment, you cannot say that it takes less than this time. If you want a perfect sorting, let's say you want approximate sorting or something. Yeah.
But as per the quantum, the environment and the basics when we study, it says it reduces the time and then reduces that, right? Is it something a technique it uses, or it reduces the n log n time?
It does not reduce n log n time because see, quantum and any randomized algorithm. Okay, by the way, here I mean a deterministic algorithm.
Oh yeah.
Okay, here I mean a deterministic algorithm.
Right.
So a quantum technically does not reduce the n log n time if you want a perfect sorting. Okay, if you are saying that you are willing to trade some quality of the sort, so it's okay as long as some of the elements are not sorted properly, then quantum could help you. Then quantum computation could possibly sort it faster, but at a reduction of the quality of the sort. Okay,
Okay.
so
Just
that's
like the PCA we do in
yes, 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 yes.
just like a PCA.
Yeah, so,
The unnecessary part we
somewhat
just
like PCA. In PCA, I think because of the dimension reduction, you will have a loss of
yeah.
quality, right?
Right.
So similar, somewhat similar to that, since
So that feature we'll have in quantum computing, but it's not like exactly it's reducing the time. So probably we have the feature where unnecessary can be removed so that we can reduce the time. Is
yes,
that the
yes, 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 yes. Some loss in quality will be there.
okay?
Okay, but if you say you want the exact answer, then you can't do better than n log n. The best,
Okay.
the quantum computer will need to behave like a classical computer in order to do perfect sort.
Just we can tweak the algorithm. That's it. The feature we have available in quantum computing is to tweak the algorithm so that it reduces the time.
Yes, 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 yes. The biggest problem will be because not a this is not a decision problem. This is a search problem. Yeah, this is not a decision problem.
Right.
So that is causing that bottleneck here. So that's the reason. Yeah.
And by the way, is this the second session, Babia?
Yes, yes. This is the second one. So next one
So
will again
I
happen on
think
Tuesday.
unfortunately I didn't receive any email alert for the last session. I'm not sure that's what I was
Yeah,
saying.
that's quite strange. Yeah, yeah, yeah.
Today again I got it.
Oh, you
Today I
got
got
it?
and
Oh, okay, okay, okay.
yeah, today I got and then thanks for your alert
Oh, yeah,
at the
yeah.
right time.
Sure, no problem, no problem. Yeah, yeah, yeah. Good.
Thank you, Babia. I think it went fine today. Very well.
Okay, okay. Thank you. Yeah, thanks for attending, Kishore.
Thank you so much. Bye.
Yeah, good.
Thank you.
Thank you so much, sir.
Yeah, sure. Thank you, thank you. Okay. Bye bye. See you next week.